Mr. Haas. We're going to talk about series.
Oh, I love series.
I know, I do too. So, series and sequences are integrally connected, however you say that word. So, here I go. I'm just going to write a sequence. Sequence.
Ah,
I'm thinking I see a pattern
Oh, that's
there.
a good one.
Yeah, it is,
Yeah,
right?
yeah.
It's not arithmetic, not geometric, but there is a pattern. So be thinking about that out there in the viewing audience. All right, this is a little dangerous. I forgot my protective equipment. But Mr. Haas, you might want to step back. I'm going to transform this sequence into a series. Are you ready?
I'm ready.
Okay. Again, it's a little scary, but here I go. Drum roll, please.
So usually you wear protective equipment for this?
I do.
Do you?
Boom! There it is.
Yeah.
Yeah.
Oh.
So a series is a sequence of numbers that's added up.
Huh.
That's really it.
That's it.
That's
the
it.
only difference.
It's the only difference.
How do I always get them mixed up. How do you remember that the series is the one where you add things? How do you remember that?
I don't
some
know.
like
Do you
way
have
of
a way of remembering that?
Sequence, you don't add them.
You don't add them.
It's just a list of numbers.
It's just a list of numbers.
Series,
Series, you add them up.
you add them up.
So
All right.
not only would I write it like that, but lots of times you actually find the sum. So I'd actually, if I said evaluate this series or find the value of this series, you'd add it up. So let's see, I'm doing some quick arithmetic. Is that 90?
I believe you.
I think
Yeah, all right,
it is.
okay.
Good. All right, so I don't want to make light of these series because they are used for some pretty powerful mathematics, but we're just going to play around with them today. We're going to come up with some notation, which is very impressive looking. If you want to impress your friends and family, have them come and watch you do your homework tonight.
Series actually are important. I mean, in computer
Yeah.
science, I was talking about it with some students, and it's a way of analyzing how efficient some programs are. It's like
Absolutely.
looking at how some series increases with running different types of algorithms to sort numbers. Actually, so,
Absolutely. Yeah, they're used in so many
People
different
really
ways.
use this stuff.
It's used in
Yeah.
statistics, it's used in higher level math. All right, so here we go. Here comes the notation. So I could write this out by hand, but we have a notation for series because these things can be long, right? They can even be infinitely long,
Wow,
these series.
that's long.
All right, so I'm going to use a Greek letter, that is the capital sigma, and that implies find the sum. That's what that Greek letter means. So let's say I wanted to express this particular series in sigma notation. Sometimes it's called summation notation. All right, I'm first going to come up with an explicit rule, an explicit equation that would create this sequence of numbers. And I'm thinking I'm seeing the perfect squares,
Yeah,
right?
they look like it.
2 squared, 3 squared, 4 squared, 5 squared. So I'm going to pick any letter. I'll just use K and say it's going to be integers squared. So I tell the world where I want to start, what integer I want to start with by writing K equals. Well, I want to start this series by plugging in a 2. So I'll say K equals 2. Now the way this works is you plug in a 2, get 2 squared, that gives you your 4. Plus, then you go to the next integer, 3, 3 squared is 9. Then the next integer, 4 squared is 16, 5 squared is 25. My very last integer to plug in, to substitute in, is 6, so I put the 6 up top there.
So it's always written like that doesn't have to be K. You can put
Doesn't have to
any
be
variable
K,
you
it
want,
could
but
be
you always.
N. In fact, they even sometimes use the letter I for this. It's not an imaginary.
I see.
You can pick any
But
letter
you
that
always,
you want.
it's always like some variable equals something on the bottom,
Right.
and then there's like a little equation in the middle, and on the top is the last number.
Exactly right.
And is it always, so series are always like counting by ones? That's kind of
Yeah.
implied? It has
It's
to go by
implied.
ones.
It's implied that you're always going up
I
by
see.
ones and always going through the integers. There you go. Isn't that
So
kind
you
of
plug
fun?
in a 2, you plug in a 3, you plug in a 4, you plug in a 5, you plug in a 6, you're done. That's what
You're
that means.
done.
Okay, I
Yeah.
got it. I think I got it.
Yeah.
I'm
Now let's try-
learning a lot here, Mr.
Yeah, I know.
Okay.
Let's try another one. What if I gave you, and I can throw something in front of a sigma. So let's use P And let's say we're going to start with, I don't know, 4 and go to 6. This is going to be a short series. And my rule is 2p. 2p.
All right, I got it.
Okay, so
All right.
let's generate this series.
All right, so let me see if I can do this. So
All
you
right.
start with the guy in the bottom there,
Yeah.
right? You stick in a 4 for p, so
Okay.
that's 2 times it's 8, I think.
8.
2 times 4 is 8. Then you
Good.
stick in a 5. 2 times 5 is 10.
10.
And then you stick in a 6. 2 times 6 is 12.
Good. I hope I'm not going off the screen
And then, no,
here.
you're fine. And then you got that 5 hanging out in front. I guess that means multiply
Yeah,
everybody
sure,
by that?
Sure.
All right.
Absolutely. Very good. It is kind of intuitive. So let's see. That gives me 30. Did I do that correctly?
Yeah, that looks good.
And then 150. So you just evaluated that sigma notation. Start with the 4, plug in the 4, plug in the 5, stop by plugging in the 6, and there you go. Now what you're going to be doing in a little bit is you're going to be generating series given the notation and then going backwards. Now when you go backwards, there, as is often the case in math, there are going to be lots of different ways to do it. So for example, if I gave you the series, I don't know, 5 plus 7 plus 9 plus 11 plus 13. And I said, write this with sigma notation. There's an infinite number of ways to do that. But generally speaking, you know, you can even use your knowledge of sequences to help you come up with an explicit equation. I see that this is arithmetic. It's going up by 2s. You can even use your handy-dandy little kind of arithmetic sequence model that we came up with. Your starting term plus your common difference times n minus 1, right? That's going to generate this series. So let's see, I decided to use n. So to end up with a 5, I'm going to start by plugging in a 1. So I'm going to put a 1 down there. 5 plus 2 times 0. When I plug in a 2, that's going to give me my 7. When I plug in a 3, that will give me the 9, 4. So it looks like I'm stopping by plugging in a 5. Make sense?
That works.
The one thing that is sometimes confusing is this number up here does not tell you necessarily the number of terms, right? It's the last number that you stop with.
It's the last number that you plug in.
It's the last
Right,
number that
I
you
got it,
plug in.
sure.
So here's a series. I'm not going to add these together. I mean, you'd have to get a common denominator and everything, but I want you to write this with sigma notation.
Oh,
Yeah.
yeah.
So, hey, why don't you pause the video, not you, Mr. Haas, but you, the viewing audience, and see if you can write this one in sigma notation.
Yeah.
Okay. So, let's see. I'm not seeing this as arithmetic or geometric or anything like that, right? And sometimes it's interesting. Sometimes we look at the whole number and try to see a pattern, but I'm not really seeing a pattern from 3/4 to 4/5 to 5/6, but I am seeing a pattern in the numerators, if you will. And I'm seeing a pattern in the denominators. See what I'm looking at here?
Yeah, going up by 1.
Yeah. So, what if I called this numerator, give me a letter, Mr. Haas.
A.
A. So what if I called that numerator A? If that's the case, that means I would want to start with a 3. So if I'm substituting in a 3, that would give me a 3, and how would I make that a 4?
I think that's an A plus 1,
I
I
think
would
you're right.
think, yeah.
I think you're right.
Sure.
Let's see if that would work. So when I plug in a 3, that gives me 3/4. Then I would plug in a 4, that would give me 4/5. I'm liking this. Plug in a 5, 5/6. Plug in a 6. I keep ending on 6s. What is, there must be
I
a
don't
meaning
know,
behind
yeah.
this. 3, 4, 5, 6.
Yeah, that works.
It does. Very nice. Now, could I have done it a different way? Well, sure. If I wanted to, I could have said, well, let's call the denominator C. And let's say
Okay.
we start with the value of c.
If you're gonna wanna subtract one
So
from the
then
top
the
there,
numerator
yeah,
would
sure.
be c minus 1. So I'd be substituting a 4, 5, 6, ending with a 7. Lots of different options. All right,
All right,
there you go.
looks
There's
good.
sigma notation.